This lesson's about resistivity, and here are your objectives. If we go back to our water analogy, water flowing through a longer pipe or a narrower pipe encounters more resistance to flow. Similarly, for a wire, the resistance is proportional to the length of the wire, and it's inversely proportional to the cross-sectional area. That's what this A means, cross-sectional area of the wire. And you can think of that as just being because there's more material in the wire for the electrons to bump into. Putting those together, we get that the resistance is proportional to the length over the cross-sectional area. And we can turn that statement of proportionality into an equation by introducing a constant of proportionality that we give this symbol to, and that is the Greek letter rho. It's not a p, it's a rho. So resistance is equal to rho times length divided by area. And you can see from this that because on the left side we have units of ohms, and on the right side we have meters for length and meters squared in the denominator here, then the units for resistivity have to be ohm meters. Not ohms divided by meters, but ohms multiplied by meters. And conductors have low resistivity. They'll offer low resistance for a given length to area ratio, whereas insulators will have high resistivity. To give you a sense, copper, which is a good conductor, has a resistivity of 1.72 times 10 to the negative 8 ohm meters, so very small, whereas wood, which is a good insulator, has a resistivity of about 10 to the 10 ohm meters, so huge differences in order of magnitude. So that's resistivity. In summary, there's three ways you can change the resistance of a wire, or more broadly speaking, a component. You can change its length, you can change its cross-sectional area, both of those are changes to the geometry, or you can change what the wire is made of. That changes its resistivity. Resistivity is a property of the material itself.